Wayne State University is located in Detroit, Michigan. In the College of Engineering, we have 2,700 students. 1,700 of them are undergraduate, and 1,000 are graduate students. We had a cluster hire last year in the area of nanomedicine and nano devices. This is a very exciting new area, and National Nano Initiative, basically dedicating the first 10 years to study and understand nanomaterials, nano devices. The next 10 years is to apply this technology into products.
NUE grant is a grant funded by the National Science Foundation, and it's called Nano Engineering Undergraduate Education Grant, and we're going to use this grant to create an undergraduate certificate program in nano engineering. Michigan has the traditional, it's very strong in traditional manufacturing-based economy, but it's also promoting a knowledge-based high-tech industry. So for that purpose, we are partnering with Michigan-based companies to create a new teaching program that would give student knowledge on nanotechnology, on high-tech areas that would be consistent with the demands of the manufacturing companies as well as high-tech companies.
This is a campus-wide initiative that a technology like this will break boundaries, silos between disciplines.
Now the world has changed. You're bringing together different expertises and different approaches to collaborate, and that's where the true advances can be made.
We have recently received a multi-million-dollar grant from the National Institutes of Health to come up with a nanotechnology solution for the treatment of breathing problems associated with spinal cord injury.
We discovered years ago a drug called theophylline. The problem is we had these side effects. Not because we were stimulating the system that we wanted, but because we were stimulating everything else, and that was causing all of the side effects. So with nanotechnology, we could selectively target only the centers that we were interested in.
We conjugate the drug molecules to the nanoparticle as well as a targeting transporter protein. So what the transporter protein does is now it will only direct the drug molecules to go to the injury sites or the neuron sites that would benefit from the drug, and the drug molecules will not be broadly distributed in a human body.
The communication between these two different worlds, understanding what they are capable of doing and putting that in reference to your interest is extremely important, I think, and it'll enable us to go to a place where neither of us could go alone.
We have an NIH R21 that is a collaboration with Dr. Yang Xu of the College of Engineering, and this project is to look at interactions between breast cancer cells and lymphatic microvascular endothelial cells. And we've developed 3D models that we can use to image those interactions. And we use the confocal microscope behind me to do that, which has an incubator on it. And we're trying to develop these models to use for screening therapies, drugs, or other types of therapies that could be used to prevent those interactions.
There's a lot of questions which requires biologists to do not one experiment, but thousands, tens of thousands, hundreds of thousands of experiments. With microfluidic devices, what you can do is you can consume a lot less reagents, you're consuming a lot less material, so that brings down the cost, And also in microfluidic devices, you can start to do these assays at a much faster pace.
Wayne State University is really the global leader in terms of using these systems and training investigators.
We need to broaden our horizons and open yourself to new ideas and new approaches that you yourself might not be an expert in or even understand.